So, iteratively through time, chemists have been developing theories to help understand the world around them. And you can think about this in terms of things that you've learned, like valence bond theory, where we looked at the electron configurations of different atoms, and we said they have s and p and d and f orbitals, and we can think about them on an energy diagram and locate them based on their position on that energy diagram. And then the extension of that would be moving into molecular orbital theory. And then now what we're going to talk about is something called crystal field theory. And it is the precursor to the thing that is really important for you to understand in this course, which is ligand field theory. But again, I think starting with crystal field theory is a useful exercise for your level of understanding. So we can think about this if you consider a metal like iron 3 plus. So if you were to go to the periodic table and look up iron 3 plus, you would find iron is the 8th element on the 3rd row of the periodic table, and it has 8 valence electrons, but in its 3 plus oxidation state, we know that that means that there are 5 electrons instead for iron. And if we were to draw this on an energy diagram, we know that the first 2 electrons lost came from the s orbitals, and the next electron came from the d orbitals, so the only valence electrons then for iron are going to be those 5d electrons. So we know that when iron is just by itself, in a vacuum, for example, that this means that we have our 5 degenerate d orbitals, and we would place electrons in those 5 degenerate d orbitals, all going in the same direction. Okay? So this would be for iron 3 plus, and this is just a single iron 3 plus atom in a vacuum, or iron 3 plus ion in a vacuum. Now, if we were to consider the iron 3 plus to be in an electric field, this is kind of getting into what's called crystal field theory. So if we were to assume that ligands can donate electrons from all different directions to that iron 3 plus ion, then what we would imagine then is that, so we would still have our iron 3 plus, but since ligands could theoretically come from all different angles to surround it, then we can think of iron 3 plus as being surrounded by a bunch of negative charge. So we can consider this to be like a crystal of electrons surrounding this iron system. Okay, and the shaded in region there is just meant to depict a negative electric field being placed around this iron atom. So we can think of each little shaded region as just a series of electrons to depict where other substances might come from. And we know that all ligands are electron donors because they're Lewis bases, and the iron center is going to be your Lewis acid, which is accepting electrons. And if we were to consider this as just an electric field coming in from all angles, then since these are negatively charged and we had our 5d electrons, remember that electrons repel one another. And this would cause the energy of those 5d electrons to be increased. So now our 5d electrons would be at a higher energy level, and we would place those electrons, again, still all going in the same direction to satisfy Hund's rule. Now, if we know, though, however, that iron, especially these d orbitals, have some directionality to them. So amongst these d orbitals, we have the dz squared, we have the x squared minus y squared, we have the xz, the yz, and the xy. Okay, so because it only has those orbitals with which to make interactions, and those contain directionality in three-dimensional space along the z-axis, the x-axis, the y-axis, and somewhere in between, then really we can, instead of thinking of this as being a crystal field that surrounds it, we know that ligands can only come in from certain directions. Okay, and the most common example of that, the most coordinatively saturated way that this can happen would be octahedral, in an octahedral coordination environment. So we would still have our iron 3 plus ion, but now instead of electric field coming in from all directions, we know that those electric fields would come in along these different axes. Okay? So along these different axes is where those electrons would come in. And we know that ligands are acting as a sigma donor. That is true of all ligands. So ligands are Lewis bases, which are electron donors, and those are all acting as sigma donors. So therefore, we can think of each ligand when it comes in has just a point charge where there are 2 electrons inside. Okay, so if we think of this being sigma symmetric, then we can draw, instead of this entire electric field around it, then we know that when the ligands come and surround iron 3 plus in this octahedral environment, that instead of being completely encasing it, it was just these point charges. Okay, so now we can start to think about what sort of interaction is happening between the d orbital electrons on iron 3 plus and the sigma donor ligands that are coming in this octahedral coordination environment. So recall that dz squared would look like a dumbbell with a donut around it. Okay, so I'm just going to draw it like this, and I'm not going to draw on the phasing because it doesn't really matter so much for our purposes right now. And remember, that sits on the center of the iron 3 plus. So we would have our dumbbell with the donut around it. And as you can see, these are going to interact exclusively with the ligands at the axial positions, so top and bottom, along that z-axis. All right. Similarly, remember that the dx squared minus y squared looks something like this, where you have shading in this region. And those lie along these bond axes. Okay, so along the bond axes that remain, that is where our dx squared minus y squared is. All right, so because of that, remember there are electrons in there which are negatively charged, and coming in from the ligands are donating of electrons. So since electrons repel each other, that is going to push those 2 orbitals up in energy. And when that happens, we get these 2 brand new orbitals that have been pushed up in energy that now reside a little higher. All right, so now consider the dxy, the dyz, and the dxy. Remember, all of those ligand orbitals lie in between these axes. So remember, if we had the z-axis, the x-axis, and the y-axis coming in and out of the screen, then the dxz, for example, lies in between these axes. So that means it lies in between where these ligand point charges are coming from. So as a result, they're not going to be excited because there's going to be no repulsion because they're out of phase with the lobes of those d orbitals. So because of that, those remaining 3 orbitals that correspond to the xz, the yz, and the xy are lower in energy, because remember, these correspond to the x squared and the x squared minus y squared. Now, this is crystal field theory, where we're considering different point charges. We're not considering anything else that has to do with these ligands except for the fact that they're point charges coming in, and this is the type of orientation and a d orbital splitting pattern that would occur, specifically for an octahedral coordination environment. And now we have an energy difference between these orbitals. And in fact, they're so important that we call them delta O for octahedral d orbital splitting. Okay, and the O corresponds to octahedral in this scenario. So now that we see what can happen when things come in octahedral coordination environments, you should be able to do the same for tetrahedral or square planar coordination environments. And these are the things that we'll talk about more in class. So this energy difference that arises from the crystal field stabilization energy, which is what it's called, happens when you consider those ligands coming in an octahedral coordination environment. Importantly, you get a stabilization or a lowering of energy in the downward direction, and an excitement or destabilization in the upwards direction. And you can actually do a calculation for this to determine what is the overall stabilization that occurs when you consider the octahedral coordination environment. So electrons that populate these what are called T2G orbitals are experiencing a stabilization or a lowering in energy that corresponds to 0.4 of whatever that crystal field stabilization energy is. So that corresponds to these T2G orbitals. And you experience a destabilization when you go in the upwards direction to what are called the EG orbitals. So we'll talk more about those Mulliken symbols or irreducible representations shortly, but just keep in mind these are called the T2G, these are the EG. So these correspond to the T2G orbitals, and you experience a destabilization for the EG orbitals that are 0.6 of that octahedral splitting energy. which means that we can do calculations to determine what happens to the electron configuration and how stabilized or destabilized something is as a result of its octahedral coordination environment. So consider, for example, remember iron 3 plus has 5 electrons, which means that we can populate our d orbital splitting diagram. And we can consider this like satisfying Hund's rule, where we place all 5 of the electrons in all 5 of these orbitals. So in this example, where you have electrons populating the lower energy states and the higher energy states, this is called high spin. And it's called high spin because it's populating the higher orbital energy set. Now, if we were to have a significant crystal field stabilization that occurs, then what would actually happen here is that these orbitals would be even lower in energy for the T2G and even higher destabilized for the EG orbitals. And in this case, because you have a greater crystal field splitting energy, now we still have our delta O, but it is significant enough that this stabilization allows for you to populate all 5 of those electrons in the T2G orbitals. And the reason it wouldn't here is because remember that electrons repel each other, so you have electron pair repulsion that occurs if you put extra electrons in the same orbital. However, if the energy that's experienced from lowering these T2G orbitals is significant enough, then it will be a stronger force or a stronger stabilization in energy to place them all in these lower T2G orbitals. And we can think about this as to what would happen if we were to do this calculation. So for crystal field stabilization energy, we can actually perform a calculation for both the high spin and the low spin scenarios. So for the crystal field stabilization energy, I see that there are 3 electrons in these lower energy T2G orbitals. And remember, I said that those get a stabilization of 0.4. So remember, that's a negative value because it's lower in energy. So I would say that there are 3 electrons there. They are experiencing a stabilization or a negative energy value of negative 0.4 delta O. And that is added to the 2 electrons in the EG orbitals, which are experiencing a destabilization or a positive energy of 0.6 delta O. Now importantly, in this case, when we only have 5 electrons, 3 times negative 0.4 is negative 1.2, and 2 times 0.6 is a positive 1.2 times that delta O. And this ends up being an overall value of 0. So in this case, for a 5 electron system, the crystal field stabilization energy is 0 in the high spin state. Now, if we were to do this same calculation, but this time for the low spin scenario, we could calculate the crystal field stabilization energy, CFSE for short, as 5 electrons, negative 0.4 delta O. And then we could do this calculation and see that we end up with a stabilization of 2.0 times whatever that delta O value is. Now importantly, this is only for a 5 electron system, and it also doesn't take into account any other sort of ligand interaction except for that sigma bonding when we consider the ligand acting as just a point charge that is sigma symmetric. Shortly, we'll talk more about what happens when you do consider other types of interactions, because while it's true that all ligands are sigma donors, some of them are either pi acceptors or also pi donors. As I mentioned, as we consider different models, we can begin to develop new, more sophisticated theories to explain the way the universe works, particularly for molecules. And I mentioned this in the context of valence band theory leading to molecular orbital theory, leading to subsequently band theory for extended solids. And also, as we've learned about in this video, crystal field theory. An extension of crystal field theory in a much more sophisticated model is ligand field theory, which considers the interactions between the metal and the ligand. For these examples, remember we're still just looking at an octahedral system, and later we'll look at tetrahedral and square planar, which are the 3 most common geometries for coordination complexes. Remember that I mentioned that all ligands are sigma donors. So all ligands are sigma donors, where they have 2 electrons that donate in a sigma symmetry. So we can redraw this, if we're just thinking about the sigma interactions, as I mentioned previously, as looking at these as different point charges with sigma symmetry. And for this, what we can do is generate the complete molecular orbital diagram to look at what is happening between the ligands and the metals. And in fact, this is what we'll do using everyone's favorite symmetry-adapted linear combinations of atomic orbitals, or SALCs. So if we recall how to do symmetry-adapted linear combinations of atomic orbitals, you start by first considering the center atom, which in this case is a metal, assigning its point group, determining what are the irreducible representations that correspond to the different orbitals on the center atom, and then subsequently looking at the group orbitals and figuring out what are the irreducible representations that correspond to that, using the reduction formula and looking up the point group, a character table, and all those things. So it's the same as when we looked at this previously, and we can start by looking at the metal center. So I know that this is an octahedral point group, and if I were to go and look up an octahedral character table, what I would find is that remember on the character table, we can assign the center atom's atomic orbitals based on that column on the character table. And if I were to go look this up, I know that I have the z squared and the x squared minus y squared orbitals, and those correspond to the irreducible representation E. So E, irreducible representation, if you look on the octahedral character table, you'll find in parentheses z squared and x squared minus y squared, which makes sense because E means doubly degenerate. The other ones would be the xy, the xz, and the yz orbitals corresponding to those d orbitals. And if I were to look this up on the character table, what I would find is that those correspond to what are called the T2g orbitals. And I'll put this down here, T2g orbitals. Now, if I were to go to the first row of the character table for an octahedral point group, remember the first row always corresponds to the s orbitals, I would find that those orbitals have an irreducible representation of A1g. Now if I go and look at the p orbitals on the character table and find those, I would find that these are T1u. And remember that capital T corresponds to triply degenerate. So all three, the px, the py, and the pz orbitals are all triply degenerate in an octahedral coordination environment. So now I've gone ahead and assigned irreducible representations to all of the orbitals, or specifically the valence orbitals, which are listed here, for a metal. And I can go and do the projection operator method and figure out what our reducible representation is for all of these ligand systems. So this is going to be for our 6 ligands. I can generate the reducible representation. And if you were to look this up in the octahedral character table, I would see that there's an E, there is 8 C3s, there are 6 C2s, 6 C4s, I have 3 C prime 2s, I have a center of inversion, which makes sense. I have 6 improper rotations, S4. I have 8 S6s. I have 3 sigma H's. And then finally, I have 6 sigma D's. 6 sigma D's. And if you were to go through and figure out, what happens to these sigma symmetric group orbitals upon doing all of these, and I'm not going to do it here just because we've done it so many times, but remember that for E, all 6 of these stay in the same location, and because of that, this gets to 6. If you were to do a C3 rotation, all of the atoms move, so for that reason, this is a 0, the next one is 0, the next one is 2, the next one is 2, the next center of inversion obviously is always 0, improper rotation is 0, another improper rotation is 0. The sigma H gets a 4, and the sigma D gets a 2. So here would be my reducible representation. And then you can use the reduction formula, just as you have in the past, to figure out which irreducible representations actually make up this reducible representation for these 6 sigma ligands. And if you were to do that, you would find that our reducible representation is made up of A1G, it is made up of EG, and then it is also made up of T1U. So now I know the group orbital irreducible representations, I know the center atom irreducible representations, and now I can build my molecular orbital diagram for an octahedral coordination complex. So what I've drawn on the screen now is an energy diagram depicting the different energy levels for our atomic orbitals on our metal and our 6 ligand interactions, which remember all ligands are 2 electron donors and all ligands are sigma donors. So remember that we were talking about iron 3 plus in all of these examples. And iron 3 plus has 5 d orbital electrons. So I can go ahead and place my 5 electrons in these locations. And I remember that all ligands are 2 electron donors, and I had 6 ligands in my octahedral coordination environment, so I should have a total of 12 electrons. So now I can build my molecular orbitals. And remember that in order to build a molecular orbital diagram, things have to match energy, but they also have to match symmetry. So what I'm going to do is go and see if I can match these up. So I see instantly that EG has a match with EG on my 6 ligands. So therefore I can come down and create my bonding interaction, which I will label as EG. I also need to create my anti-bonding interaction anytime I make a bonding molecular orbital. So I'm going to go ahead and make my EG interaction, and again I'm going to label that EG. Now the next one that I see is that there are a 1G and an A1G on my 6 ligands. Remember the A1G came from the s orbital on the metal, which is always the first row of your character table, and I'm going to label this A1G. And I also need to create my anti-bonding orbital, which I will call A1G. And then the next thing that I see that matches is that I have a T1U, and the PX, PY, and PZ orbitals from the metal correspond to T1U as well, as far as its irreducible representation. So that means that I can create my brand new bonding molecular orbital, which will be these 3 T1Us, which I will label T1U. And then I also, remember, need to make my anti-bonding molecular orbital that corresponds to the T1U. Now notably, there is no match for the metal orbitals that correspond to the T2G irreducible representation with the 6 ligands. So because of that, these are going to be non-bonding orbitals. So that means that I will just bring them over and I will create my 3 T2G orbitals, which will be fully non-bonding, so T2G. And now I can go through and take my 12 electrons here and my 5 electrons from the metal and start to place them in my molecular orbital diagram. So that means I will place 4 here, 2 more here, that's 6. I have my 3 T1Us for another 6, that gets me to 12. And now I'm left with these 5 electrons, so I have to use all 17. And now I start to see that those T2G and EG orbitals look a lot like the crystal field orbitals that we talked about at the beginning of this video, which we labeled as EG and T2G. So I mentioned that you would see why they were called T2G and EG, and this is where it comes from, because those correspond to those molecular orbitals when you make an MO diagram for an octahedral metal complex. So now, things that we'll need to consider, and we'll talk about this more in class, is whether or not this is going to be a high spin complex where the electrons do populate the EG orbitals, which are noticeably anti-bonding, or do all of them populate the T2G orbitals, which we would call low spin. So if you begin to pair up these T2G orbitals before moving on to the EG, those are called low spin complexes. And if instead you would populate single electrons in the EG before going back and pairing up the T2G, we call those high spin. And this is something that we're going to talk about more in class, because as it turns out, the energy difference for this octahedral splitting pattern, or the d orbital splitting for an octahedral coordination complex, is impacted. The energy level, the distance between these two orbital regions, actually depends on whether or not the ligands can do more than sigma bond interactions. Are they pi donors? Are they pi acceptors? And we're going to look at this in the context of what's called the spectrochemical series.